So let me just pull up very briefly the syllabus. Just take me a second. It's not prepared. I have too many computers. So I just want to talk very briefly about what we're going to talk about this semester. And again, the class will be a lot like last semester where we're going to talk a lot. We're going to spend a lot of time on theory at the beginning, building up a tool set. And actually, I like to think of quantum mechanics as a language. We're going to learn a language. And I think today we're going to learn why I call it a language, because it's going to seem very foreign. Right? It's not really a toolkit. It's not really written in English. It's not written in the words of classical physics, thermodynamics. So we're going to have to learn a new language. So we're going to spend a good amount of time on that language of quantum mechanics. So for about the first 2 weeks, we're going to talk about theory. Right? I'm going to tell you how to represent a molecule or an atom, something microscopic, and how do we interrogate it on the board or on a computer, right? A calculation. We'll talk about how it connects to the experiment as well. What we're going to want to do with those tools is to start modeling chemical systems. And one of the things that we're going to learn about molecules in particular is that there's only a small set of things that they can do. Two of the fundamental things that a molecule can do is rotate and vibrate. Right? And so we're going to talk about vibrating things and spinning things. So here module 2 is vibrating springs. Let me zoom in a little bit for those in the back. Vibrating springs and spinning tops. So we're going to talk about the mechanics of springs and tops. And we're going to apply it to chemistry, or molecules in particular. It's going to be a really, really useful set of toys to play with, because we're going to find out that bonds between two atoms can be modeled as a vibrating spring. Right? It's going to give us a model for a bond. And we're going to learn more about bonds and how they work than you can ever possibly imagine by just assuming that bonds are like slinkies. If you don't vibrate a molecule, if it's just sitting by itself, not doing anything, the only two things a molecule can really do is move in space, right? X, Y, Z translation, like a gas, or it can spin. It can rotate, like a top, right? And so we'll talk about the theory of spinning tops, and that we'll find actually that doing the physics and thinking about how molecules rotate will actually teach us a lot about how things move in orbits, circular motion in general in physics or in chemistry. And that's going to be really important, because the most important chemical kind of fundamental object we have is the atom. What is the hydrogen atom other than a proton with an electron around it orbiting? Right? And when we learn about how molecules and things rotate, we're going to be able to apply that technique directly to the case of an electron orbiting a proton. Right? And that will give us an equation. I mean, literally a set of equations I can write on the board that are the exact solution for the hydrogen atom. We'll be able to calculate anything we want about what hydrogen does. Right? We can talk about where the electron is, where its energy levels are. Anything you can think of about an atom, we can calculate. We'll be able to do it exactly for hydrogen. Unfortunately, it only works for just hydrogen. Well, we're going to want to get to helium and bigger atoms with many electrons. And we're going to come across a problem where we're not going to be able to do this exact thing anymore. We're not going to be able to write down an equation for helium. But we will have a framework in which to calculate things about helium. And that framework, which we really introduced in Module 1, is so important, because what we're going to learn, and this is different than say, billiard balls. I'll explain this in a second. Is that if you think about an atom like helium, right, which is a nucleus and 2 electrons, we're going to find that you can't write down an equation for 2 electrons and a proton or a nuclei. Not going to be able to write down a set of equations for it. But we can approximate what helium looks like by treating helium as 2 one-electron systems. Right? You have a hydrogen atom with a nucleus and electron, and then you have another one basically right on top of it. We add them together. We're going to treat helium as 2 hydrogens put together. And it turns out that works really well. It doesn't work perfectly, but we'll have a framework to how to make corrections and improve our guess. And it turns out in quantum mechanics that works everywhere. In quantum mechanics, what we say is that the theory is linear. Right? I don't have to think about this right now. We'll come back to it. What that means is that if you know how one particle, if you have a solution or some sort of idea of how the physics of one particle works, then the physics of n particles is just n solutions. You just add them together. All right, so a helium atom, in some ways, we're going to represent as two hydrogens kind of smacked together. Two hydrogenic electrons around the nucleus. That's really, really powerful because then, well, if we get the plutonium, which has something like 95 electrons, well, that's just going to be like 95 hydrogens put together. That's really, really powerful. Because in classical mechanics, with Newton's laws, if you look at how two objects orbit each other, say a moon and a planet by themselves, you can solve for that. Right? The two-body problem is exactly solvable in Newton's laws. So you know exactly how that system works. But if you introduce another orbiting species, you have a three-body problem. Say you have the sun, the earth, and the moon. You can't write down a set of solutions for that. And in fact, some trajectories, some initial conditions for a three-body system aren't stable. The moon and the earth and the sun come together in a certain way, they might just fall apart and fly away from each other. Sometimes they'll form stable orbits, sometimes they won't. And so in Newton's laws, we know the physics of one body. We can calculate the physics of two bodies, but we can't calculate any more than that. Right? We say that Newton's laws are nonlinear, which means that this theory doesn't add linearly, right? N bodies isn't just N particles. It's more complicated. The particles interact with each other. And that makes the physics very difficult, extremely difficult. So difficult, there's even a sci-fi book series from China called The Three-Body Problem, which deals with this issue. Solving the three-body problem is extremely difficult in orbital mechanics. But in quantum mechanics, it's trivial. I wouldn't say it's trivial, but comparatively, it's trivial. All right? And so we'll talk about that structure. We'll talk about how you do that computationally. And what it does is we're building a theory that allows us to do chemistry. You can think about it on a piece of paper, but really the way we do it is on a computer. Right? We can calculate things about molecules' properties and about atoms and molecules and how they interact, their reactivity, their structures. Right? And we're going to come up with a theory that allows us to do that exactly, or as close to exact as we want. That's very, very powerful. And you don't have that luxury everywhere, but we do in quantum mechanics. So we'll spend about a week and a half on the atom. And then, of course, what we want to do is put atoms together. Right? We're chemists, after all. We want to do molecules. So not surprisingly, as I told you, the way that we're going to represent a multi-electron atom is by cramming a bunch of one-electron atoms together. Not surprisingly, all a molecule is, the way we're going to tackle it, is cramming a bunch of atoms together. Right? The physics of a molecule is just the sum of all of its atoms. Right? So what we're going to do is bootstrap things. Right? We're going to start from a basic framework and build our way up and just add things together to higher and higher complexity. And so by the end of by early April, we'll be able to talk about molecules. How do they form? What kind of structures do they have? What kind of properties do they have? And how can we calculate? Finally, once we have all that together, we can now ask, well, how do we probe them experimentally? Right? How do we, we can calculate anything we want. It doesn't really matter. We can do as many calculations as you want, but if you're just calculating bullshit, it's not that important. It's just kind of irrelevant. So we need to test it. Test our calculations and test our theory. And the way we're going to do that is spectroscopy. Spectroscopy always, since the dawn of quantum mechanics, since the beginning of the 20th century, late 19th century, the way that we've understood atoms and molecules is through light. And that's spectroscopy. Spectroscopy is, for chemists, the essential connective linkage between our macroscopic eyes, our bodies, and this microscopic quantum mechanical world. Right? Light will be our guide. So we'll spend a good amount of time on light. We'll do some review about how light works, of course, and how it interacts with things. A couple of things. So that's basically the course. When we get to spectroscopy, so one quick thing for everybody. I already do technically have an assignment up. I'm sure some of you already answered it. Again, I have my introductory survey again. It's due, this is the Tuesday, due Tuesday. So make sure to fill that out. You get a free late submission if you fill it out, just like last semester. I ask you a quick question on here. We don't have time to do, with spectroscopy, we can talk about the basics of spectroscopy, but we need to apply it to something. So one thing that I'm going to ask you guys is, what kind of spectroscopy would you like to think about this semester and explore? So think about that a little bit. If you'd like to learn about a specific technique, just write it down and vote for it, and we'll pick that. Whatever one wins the most votes, we'll focus on. So I'll leave that up to you. Okay. Any questions? Okay, cool. Let's begin. I want to begin today with a very, very, very qualitative. Right, that's the wrong. Oh, that is the right page. A very, very qualitative and kind of fun discussion today that will do absolutely no math or physics or anything like that. All right. I mean, I guess technically it's a physical experiment. We're going to do a thought experiment, but we're not actually going to do any math. We don't need to, as we'll see. And this experiment, which people have done in real life, gives us a result that doesn't make any sense. Right? And I want to talk about that not making sense. Right? There's a really, really famous music documentary called Stop Making Sense about my favorite band, Talking Heads. And this is the moment where science will stop making sense to you. And that's not your fault. It's not anyone's fault. What we're going to find is that, again, even if you're not a scientist, not everyone here are scientists, they're interested in science, we naturally have an empirical way of doing things as humans for the most part. We try something and we see what happens. If it succeeds or fails, we adapt our behavior. Now, some of us are insane, like me, and we beat our heads against the wall over and over again, not learn a lesson. That also happens, but ignoring that, everything working efficiently, right? We are empirical human beings, or empirical things, and we learn from our mistakes and our observations. And that, over the years and over the generations and over the eons that we've existed as a species, we have a set of instinctive ideas of how the world works. Right? And of course, some people will kind of joke around, well, that comes from us being cave people at some point, bashing deer skulls and going unga bunga and all that junk, and having a very simple idea of how the world works, right? Or we know how a baseball flies because we whack it with a baseball bat, and the harder we whack it, the harder it flies, right? We have these senses of how physics work just from intuition. And we've built this language in our head, mental language in our head, on how to interpret physical phenomena, trajectories and gravity and all this stuff. And it makes a lot of sense to us because that's the way we've been trained to think. What I'm going to show you today is an experiment. We're going to play around with it a little bit. That will give you an answer that makes no sense to you. In fact, it'll confuse you completely. And that's not your fault. The fault is that we are not trained to think this way. And so we're going to see something that seems very, very contradictory and absurd and non-physical. And in fact, it's very physical and very true and experimentally verified time and time again for decades. Right? So everything I'm going to present today is true. But you're going to be like, this makes no sense. Right? And that's because you just don't have the language to understand what's going on here. And this is the problem that was presented to physicists and scientists when we invented all of this stuff 100 years ago. This stuff doesn't make any sense. And in fact, the experiment I'm going to show you, Einstein went to his grave not believing it. Right? Even the most intelligent people in the world, in history, at the turn of the century, thought this was absurd. All right? But it turns out that in some ways they're wrong. And even Einstein couldn't get out of that caveman-like thinking about things. And the point is that there's nothing wrong with that. It's just that the microscopic world is a very different place than what we're used to. So let me introduce what we're going to do today. Very, very simple experiment. I'm going to build, and this is something you can buy on eBay or anywhere. They used to make them, you used to have one in your home. You guys might not be old enough to have had one in your home, but I did. There's something you can buy, and it's in many different parts. I'm going to draw it in a way that doesn't look like what it actually looks like. A gun that shoots electrons. All right, an electron gun. Does anyone know where you would find an electron gun in a home? Anyone have any idea? Yeah.
Aren't they used to see if, like, where the electricity is running through, like, a wire or something?
I suppose so. That's not really what I mean here. Here we're taking a gun and we're shooting electrons through the air. So literally electron gun. These are the source of electrons and light in a old school TV, cathode ray, CRT TV. You know, those giant old ones that no one has anymore except for Super Smash Brother players. The element of a CRT, the main element is a phosphorescent screen, and it's a vacuum sealed environment, and in the back of that screen is a gun, an electron gun that shoots electrons, and the trajectory of those electrons is determined by where you need to show the pixel on your screen, right? It'll shoot an electron up in one corner if you need to have some color or some light there, and an electron somewhere else. Right? So these were a dime a dozen. Right? They made millions of these every day for decades, and now they don't make any anymore. It's really hard to find one that works, unless you go to like Russia on eBay. eBay Russian vendors still sell them, and that. So anyway, you can make these guns, all right? And if we think about how a television works, these electrons, they're particles, right? They're like bullets, all right? Because that's what happens in a TV. We want to draw a color pixel in the right corner of the screen. The electron gun shoots an electron at that point in the screen, right? It's just the trajectory, and the electron goes in a straight line and hits that part of the phosphorescent screen. All right, so that's going to be my source today. We're going to do some experiments with electrons. All right, and we should talk a little bit about the properties of electrons. So the first one that is maybe relevant, but probably not relevant, as we'll see, is the mass. Does anyone? You probably don't know what the mass is, but you'll probably memorize it by the end of the semester. It's about 9.1 times 10 to the minus 31 kilograms. That's a really, really tiny particle. The size, in terms of its shape, does anyone know what the diameter of an electron is? It's a trick question. It doesn't have one. An electron is a point. For as far as we know, electron has no shape, right? It's interesting. How can something have a mass but no shape? It's an interesting question to think about. But the size is negligible, so it's a point. It's point-like, right? People have tried and have continued to try to measure the shape of an electron, just to see if it's a damn sphere even, but it's not. As far as we can tell, it's a point. Okay. Now, already we're getting into weird places, right? I'm telling you that there's something that has no shape, no size, no physical size, but has a mass. Right? So that should already trigger something in you that this is weird. We're not going to worry about that too much because there are plenty of particles in the world that don't have shape. Right? We'll talk about that. It's point-like. Of course, electrons have a very, very important property besides their size and their mass. It's their charge. And what's the charge of an electron? It's really easy. You should memorize it. Go ahead.
Negative.
Negative what?
-1.
Yeah, -1. It's the unit of charge, right? One electron has -1 charge. Okay? Simple as that, right? And a proton is +1. We'll talk about subatomic particles next week, but right, very, very simple. There's also another property of electrons. Electrons have one other property, all right? And it's called spin. And I'm not going to use that word today, right? So instead of using the word spin, and you may know, maybe you don't know, the spin of an electron is 1/2, which shouldn't mean anything to you right now unless you're really into this kind of stuff. We're going to ignore spin today. We'll come back to it. Spin is super important, and in fact, perhaps the most important property in all of chemistry, spin. But we're not quite ready to talk about spin yet. So instead, I'm going to make up some properties that will have the same behavior as spin, but we don't have to worry about what spin is, right? And those properties I'm going to give you are binary in the sense that there's two flavors. Okay, so there are two different types of electrons, if you will. and I'm going to give them two different properties. Color, so they can either be, we'll say that they're either white or black. Right? Not a real property, just bear with me, right? Color is not a real thing for electrons. There are particles that have what we call color, but we're not going to worry about that. Let's just assume they can be white or black. And they can also have a flavor. They can either be sweet or savory. Right? And I'm just going to make sure to tell you guys that these two are bullshit properties. Right? They're not real. Just to remind you, they don't actually have color and flavor. Right? But these will be, as we'll see later, these can be analogs for spin. Spin is a binary property. Right? And it actually has two components, color and flavor, that we're representing. Okay, so I'm going to do a really, really simple experiment today. So what I'm going to introduce now is we're going to shoot electrons and we're going to put them through two different type of apparatuses, or devices, if you will, that separate our electrons based on their color or flavor. Okay, so I'm going to have two boxes. That take an electron in. We'll call it the C for color. If the electron is white, it comes out this way. And if it's black, it comes out another way. Okay? So it splits white and black into two different directions. And we're going to have another box that does the same thing. Let me demarcate this so it doesn't interfere. We're going to have a flavor box. All right, maybe I've put one of you guys inside of a box and made you taste every electron that comes in, and you tell me if it's sweet or savory. So I'll call it SAV and SW for sweet and savory. Okay, so I have two boxes. All right. Don't worry about what these boxes do. This is what they do. Don't worry about how they work. We can make boxes like this for spin. People do this all the time. I'm just renaming the characteristics to color and flavor. Okay? These boxes do exist. You can make these things that split these electrons separately like this. Okay. Let me start a new page. Let me move this over a little bit so you can see it. So let's do a couple of experiments. So let's do the first one. Very, very simple. We're going to take a random electron, and we're going to put it into one of the boxes. We'll start with color. We get white out here and black out here. And then at the ends of these lines, we're going to put detectors. Okay? So I'll draw a detector with this box that's shaded like this. These are our detectors. All right, and every time an electron hits one of these boxes, it makes a click. All right, it's like a Geiger counter. Right? Every time it hits the detector, you get a click. All right, what you usually use are CCD cameras. Right? You can buy CCD cameras that do this exact thing for electrons, and you can measure them and detect them with a camera. Okay. So now what I'm going to do is I'm just going to send in one electron at a time into this box. There's tons of them, hundreds of them. Okay, thousands. Doesn't matter. And I'm going to measure the distribution of clicks at each of the boxes. All right, so I'm not really concerned about the count of electrons that go through, but the percentage of clicks I see on either of the ends, the detectors. So what I'm going to do is this. So what I want to measure at the end are number of clicks, or percentage. Let me do percentage of clicks. And I'll explain why I don't really worry about the number of electrons in a little bit. We'll see why that's not a useful number in a second. So the number of clicks, and I'm going to ask what's the percent that are black, and what's the percent that are white? Okay, you might be able to answer this question right now, and I'm going to pose it to you in just a second, but let me tell you something else about electrons. Every electron is identical. All right, you can't distinguish between two electrons. this is kind of a weird concept, and it's kind of hard to think about classically, because when I think about, you guys are all distinguishable. This is Hyatt, and this is Danny, and so on and so forth. I could put little hats on everybody and know where everyone is. Electrons, you can't do that. Every electron is exactly the same. The only thing I can measure is how many I have. So I know that maybe I have 100 electrons, but I can't go, this is electron 1, this is 2, this is 3, this is 4, this is 5, because they're all identical and indistinguishable. Okay? Every electron is exactly the same from the other one. All right, we'll talk about that, the consequences of that later. But for the meantime, let's not worry about it. But just think of that. So you have these electrons, they're all exactly the same. There's nothing different between them. You can't tell them apart. You just know that you have some flow of them. And you get clicks. All right? They're all identical. All right? And there's no preference whether they're white or black. No preference. Totally fine. Just random. So given that, what do you think the percentages are here? 50-50. Totally right. And you go do this experiment in the lab, and that's what you get, 50-50. Right? They're randomly distributed. Half of them are black and half are white. All right, and if I change the color to the flavor, right, and then I get sweet and savory instead. Same experiment, but I'm changing the box. What do you think the distribution is going to be? Will it be any different? No. No, it's the same thing, right? They're unrelated concepts. That's another thing, is that color and flavor don't have anything to do with each other. They're completely separate. Right? So they don't influence each other, and everything's random. So 50-50. Okay. Really, really trivial experiment, but it's an important one. We just got to make sure that everything makes sense, and it does. All right, so let's make this experiment a little more complicated. And please yell at me if you want me to go back. Let me change colors. All right, so 2. So what we're going to do is the same thing. We're going to take an electron and put it into our color box and split by white and black. But then what I'm going to do is I'm going to block one off. All right, so I'm going to put a wall here so that no blacks come through. All right, the blocks just go away. And then for the ones that I filter out that come through the white channel, I'm going to measure their flavor. SW and SA, sweet and savory. And then I'm going to detect the flavor. Okay, so let's think about this a little bit. Should make sense. Electrons come through. 50% of them go this way. We lose them. And 50% of them go through here, enter into the flavor box, and then get split. And what should they get split into? What percentage of clicks should we see here and here? Yell it out. What do you think?
25.
Okay, so that's with numbers. So I'm doing percentages of clicks. So for 100 that come through here, how many percent, what clicks do you get? So you're exactly right, though, that you only get 50. So you're saying it's 50-50, right? Because there's 50 total that come through here, 25-25, right? So that's fine. That's the reason why I don't want to talk about the number of electrons, because then we got to deal with those factors of 2. But when I think about the number of relative counts, it's still 1-to-1. Okay? So what that tells me is that the colors are uncorrelated to the flavors, as we expected. Right? The color doesn't determine anything about the flavor. And the flavor, and we can flip this around, right? We could do flavor here and color here, and do the same thing, and you get the same result. Right? If you split by flavors, 50% are going to be white, 50% are going to be black. Now, here's an interesting result. I'm going to go to the next page. let's do a different experiment. Slightly different. Again, we're going to do the same thing. We're going to put an electron. Oh, sorry, that's the wrong box. We'll do color. And we'll say white comes here, and then black comes here. Okay, and what I'm going to do is I'm splitting the beams. And then what I'm going to do is I'm going to bounce them off of mirrors. Where are my pins? Let me sit down for a second. This is going to be easier if I just sit. Come on. I'm stuck on the cable. Okay, I'll do it in a second. So they bounce in mirrors, and they recombine at this top right point. So here I'm going to put a beam combiner with an X, so they combine. And then I'm going to detect their flavor. And detect. Okay, so it shouldn't be that surprising. This experiment's really no different than the last one. Well, sort of. I've split them into their two categories and then recombined them and measured their flavors. And not surprisingly, you don't have to answer this, but not surprisingly, you get the same result, right? You get 50% sweet and 50% savory. Okay, and I'm going to write here with, above it, be specific, a random electron. If a random electron, you don't know anything about it, you do this, you get 50-50. So I will mark the electron with my blue. Okay. Now, let's do something different. Let's pick the flavor of the electron to come in. All right, so let's say instead I bring in a sweet electron. We're going to do the same experiment again. Oh, sorry, I just spoiled the answer. Ignore that. Pretend I didn't do that. But it shouldn't be that surprising. And we're oh, actually, no, it's not the answer. Sorry. Okay, so I'm going to split my sweet electrons into black and white. And of course, they're 50-50. Right? So 50% go this way and 50% go this way. And then they recombine. And we measure the sweet or savory amounts. All right? What do you think the answer is going to be? What's the percent that we measure that are sweet versus savory in this situation? What's the logical answer here? What did you think about it for a second? And just yell it out if you have an idea. Okay? Remember, the electron is initially sweet. And then we're basically doing nothing to it and then measuring the flavor. That's what this experiment is. So what do you think the answer is going to be at the detector? What's that? 100%. Of course. They're all sweet, right? We've already determined that. Why would it change? Right? And if we change it to savory, if we put a savory electron through, we get the opposite result. 100% are savory. I'm going to add something now. And I'm not going to redraw this. I'm just going to label this 3A. All right? And what we're going to do with our modification in 3A is we're going to cut one of these arms off. So let's say we cut the white off. All right? So no white. Only black. Okay, so what we're doing now is actually filtering out by color. Okay, and not surprisingly, you would imagine, okay, I have the sweetness doesn't matter. So 50% of the sweet electrons are white and 50% are black. So 50% of them are going to hit this wall, right, and not go through. And so that means only the black ones come through here, and then we measure the flavor. And I'm going to ask the same question. What's the percent of sweet and savory here? Any suggestions? I heard a 50-50. Right? Is that what someone said? 50-50? Does anyone disagree with that?
Are you going in with the sweet electron? How are we getting a savory out of it?
Okay. So you would say it's 100-0, right? Yeah. Okay, so actually, yeah. So let me ask a different question. Why, whoever said 50-50, where am I? Okay, it's good. Whoever said 50-50, why is it 50-50?
I didn't realize we were doing the sweet electron.
Oh, okay. Okay,
Electron.
you're right. If it were random, you would be right. 50-50, right? But it's a sweet electron. So do you agree it should be 100% sweet? I'm going to write down what the experimental answer is. It's 50-50. You lose that information. It's no longer sweet anymore. That should be a problem. That should trigger something, right? We've just gone through a very, very kind of meticulous logic, very, very simple logic about how this is going to work. And the moment I block this, and I only pick one, right? What I'm doing here is I'm taking sweet and then only pulling out the sweet black ones, the licorice electrons. Not the white chocolate, but just the licorice, or the, darkened white chocolate. I like licorice more than chocolate, so I'm going to go with licorice. You only take the licorice ones and then measure the flavor, and now the flavor is completely lost. You get 50-50. People have done this experiment with electrons, atoms, molecules, buckyballs, mirrors, actual mirrors. You get the same result, 50-50. It gets worse than that. All right, so first of all, this should already be a problem, right? And we're going to have to deal with this problem because this is the first indication that not all is right with the microscopic world. I say that, but it's not the microscopic world that's the problem. All is wrong with your head at this very moment. Quantum mechanics is about beating yourself. It's not about learning how the world works. It's about how to unlearn your hypotheses about how the world works. We need to keep that. It's a fight against yourself. But this is the exact result, 50-50. Every time you do this, anything you put in front of it with this experiment, any type of color or flavor, any type of property you can think of, 50-50 is exactly what happens here. This is a real problem, and it gets worse. Let's imagine that the arms of this experiment are super long. Let's say that the color box, the electron gun and the color box are on Earth, and the combiner is at Vega, which is at 40 light years away. It's a bright blue star 40 light years away from us. Right? It takes 40 years for light to get there. And our flavor box is in the center of the Milky Way. All right? That's hundreds of thousands of light years. Okay? So let's think about, so what does that mean? So first of all, let's think about the rate at which things communicate here. Okay? We have electrons moving, right? They're moving over physical distance from Earth to Vega to the Milky Way center in this experiment. They have a velocity. Because they have a mass, they can't go at the speed of light, right? The only thing that can go at the speed of light is light. So the electrons are moving at slower than the speed of light. But what would have to happen in order for the electrons to somehow lose that information, right? That the sweet information, which you see here, is now lost in the Milky Way center. right? Somewhere that information about that electron has disappeared from us, right? It's reset. Okay, so let's assume, again, the electron is moving at some speed that's slower than the speed of light. And that information, right, when Earth communicates with Vega with the Milky Way center, that information travels at the speed of light. So the information, so when Earth gets that electron and sends it out, it can send a message to Vega to say, hey, electron's coming in 40 years, or in 45 years, or however long it is. And Vega will be ready to prepare for that electron, because the electron takes longer than 40 years to get there. Okay, so Vega knows the electron's coming, is ready to go. Right? And that's the case everywhere here, right? The information is traveling at speed of light, but the electron is traveling at sublight velocity. So let's imagine that the Earth, on January 1st at midnight, Greenwich Mean Time, every year sends an electron out. All right? And somewhere, and there's some homies, some construction dudes out on a ship, somewhere between Earth and Vega, say 20 light years away, maybe near Proxima Centauri, which is 4 light years. They're sitting here with that concrete barrier, and they're going to move in and out. Okay? So year 1, we do the experiment, and we allow the electrons to pass through. Okay? There's no block, right? So we're doing experiment 3, not 3A. And what do we see? 40 or 60 or a million years later at the Milky Way center, that they're 100, 0. Right? And they're all combined through here. All right? What does that mean? Well, that means when the electrons leave the Earth, right here, they're sweet. Okay? I think we can agree with that. There's the sweet electron here, and we saw that if you put a sweet electron through a color box, it's still, there's nothing to say it isn't sweet anymore. All right, so let's imagine that we send this electron out again. And somewhere where the electron is, right, after the electron leaves Earth, but before it gets to Vega, our construction homies come in with their barrier and put the barrier here. Okay, so the electrons, the white electrons, are somewhere here. Right, they've already left down this path. And the black electrons are on their way as well. All right? So the white electrons are leaving Earth, and they hit that wall. Okay? And, well, they're gone. And then, 40 years later at Vega and the Milky Way center, they measure the remaining electrons that get there. And what do they find? Well, they're 50-50. That should be odd to you, because nothing about this experiment has changed. Midway through the experiment, I added a wall. Right? All the electrons are doing here are just moving. Not only are they just moving, they're light years and light years away from these. Right? You can imagine maybe this is going to Pluto and then out to Vega, but this goes around the sun the opposite way out to Vega. Right? So these paths are really, really far apart. And so at this point right here, they're 100% sweet, or at least we think they are. But somewhere in the trajectory here, these black ones, which we thought were sweet, have now mixed. Because these electrons that have hit the wall light years away have hit a wall. How the hell do these electrons know that these electrons hit a wall? They're light years away from each other. So what's happened is that somewhere in this region right here, all that information is lost, and it's lost at a rate that's faster than the speed of light. Imagine we put this wall here. Maybe we put it right here. Imagine we put the wall in 1 second before the electron arrives to Vega. Maybe 1 minute. All right, so the electrons are like right here. At this point, there's nothing stopping it from saying it should be 100, 0. That's the result we should have. They're about to be recombined. And then right before one of these, say the white electrons get there, we put the wall in, and then measure the ones that come out, and then instantaneously they've gone from 100 to 50-50. What that means is that it turns out that the information, the savory sweet information, has propagated from this event, the blocking event, to the other electrons in the system faster than the speed of light. And you can prove this. You can do it in lab. You can show you have two electrons moving at some finite velocity, and they're moving at some distance that's way faster than your way longer than your communication time. Or sorry, they have to move at a much longer time than the time it takes to communicate between the beginning and end. And what you find is that somehow the electrons, despite the fact that they can't actually communicate to each other within the amount of time through the speed of light, they have communicated with each other, and the result is as if they've talked to each other, and they've mixed again. So what happens is that what this appears like is that communication between electrons in these two paths are actually happening faster than the speed of light. That these electrons up here know what happened here instantaneously. But that has to be impossible because they're light years and light years apart. It would take years for these electrons to tell these electrons what happened. But it happens instantaneously. There's a term for this. Well, there wasn't a term when it was first invented. But Einstein, our man who is very curmudgeon and somewhat sarcastic, and I'll write it on the board, come up with a term. He wrote this in a letter when they realized that this is actually what happens. Einstein called this spooky action at a distance. Right? It's like as if the electrons can talk to each other faster than anything else in the entire universe can talk to each other. That information is transmitted in this experiment faster than the speed of light. Because that's the only way you can describe these changes. Einstein was not happy with this, right? This is not a, what would you call it? This is not a compliment. Because Einstein's a realist, the last thing he wants to talk about are ghosts or supernatural abilities, supernatural events. But to him, it's very supernatural. Right? By definition, it's supernatural because, as Einstein proved, the fastest you can ever move is the speed of light. But here's an experiment where things move faster than the speed of light, or rather, information is transmitted faster than the speed of light. So he says it's spooky action at a distance is the term he uses. And in fact, this term is now ubiquitous. It doesn't even get translated. I had a Russian PI in my postdoc, and he had his girlfriend. She was a ballerina, an opera singer trainer, and she came to visit our lab, and they were talking in Russian with each other, and I was just sitting there working, and he's talking in Russian with her, and then I hear him say spooky action at a distance in this Russian accent. And he told me there's no Russian term for that. They use the English term, so it's actually a universal term. Einstein went to his deathbed convinced this is bullshit, that this is not real. What Einstein thought, right, is that there's that there's something encoded inside of the electron that determines this, right? That the electrons, when they pass through here, already know they're going to be 50-50, right? They have some kind of encoding that gives them this behavior to kind of mix up. He calls them hidden variables. Right, that these electrons have some properties that we can't observe that allow them, basically they don't have to transmit the information across faster than the speed of light. They already have that information built into them. We can't measure it ourselves classically, but they have, right? These hidden variables or local variables. And he wrote a paper with two other guys, Podolsky and Rosen, called the EPR paradox, where he assumes that there are no local hidden variables. Right? That the electron is as stupid as we think it is. And he shows that it leads to a paradox. And it turns out Einstein was wrong. Maybe a couple decades later, a man named John Bell came up with a theorem that said that he comes up with a way to experimentally test whether electrons have this hidden information inside of them, these hidden variables. And John Bell proves, and through experiment later, in the 1980s, that electrons or quantum mechanical particles don't have this information. They act as if they're stupid. That this experiment is precisely what happens. The electrons somehow magically transmit information across not state lines, but universe lines. Right? I can take this limit, right? I can go to billions and billions of light years. We can do it over a galactic scale, and the result is exactly the same. We can do it in a lab. The result is exactly the same. People have done it between the Earth and satellite. Same result. People have done it across cities through underground fiber optic cables. Same result. It doesn't matter what length scale you're at. Electrons transmit information at the faster speed of light. They're not actually doing that. So here's the important thing. This is the important lesson that I want to teach about this, is that by saying that things are transmitting through the faster than the speed of light, information is being mixed and communicated in this absurd way. Well, it is absurd. It's not physical. That's not actually what's happening. The problem is that we're sitting here thinking about electrons like they're billiard balls. Right? Billiard balls with some characteristics. A piece of food or a piece of candy. They're not. The problem is not with this spooky action. That's actually how the world works. It's just that what we see here in the macroscopic world, in our physical world, things that we can see and touch, violate this principle. These little effects are all washed out. We don't observe them. They're microscopic. They only become important at the smallest limit. And so the problem really isn't this idea of communicating information across faster than the speed of light. That's assuming these particles are acting like they're particles, like we know and love. They're little balls. They're not. They're not at all. Right? So we have to get away from that. We have to get away from the assumption, thinking of things about like billiard balls. But we have to think about electrons. They're not billiard balls. They're not charged billiard balls. They're electrons. And electrons do this. And so we have to build up a new world where we understand how this works. And there's an answer to this that's very logical of why this works the way it does. I can show it to you on the board. We can talk about it. I can show you that this is what happens. And I can show you that there's an entire class of properties that a particle may or may not have, or an object. We'll say not a particle, but an object, like an electron or an atom, that exhibit these kinds of properties. These ideas of things being ephemeral, right? That properties only exist for a short amount of time. That's not really what happens, but that's kind of what this looks like, right? It looks like it's lost, right? It looks like this electron has lost its sweetness. It hasn't lost its sweetness. Our problem is our assumption of assuming it's sweet to begin with. All right? So it's actually, the problem is this right here, our assumption here. This is not, the electron is not just sweet. There are not sweet and savory electrons. It's not the way it works. Electrons can be either sweet and savory, and sometimes they can be mixes of both. Right? And there's this concept that I'm going to introduce in this class, probably in the next couple of lectures. You've probably heard it before, called superposition. Superposition. It's kind of hard to explain before we will talk about waves. That's where we first learned about superposition, with waves. And maybe you've heard of this concept of a wave-particle duality, and that particles, electrons, are waves and particles at the same time. The actual answer to that is that electrons are not just waves or they're particles. They're not both, and they're not neither. They're a combination of the two, and you can't, it depends on how you interact with them, whether they look like waves or particles. They're both. But it's not like they're either or. It's not an either or statement. It's an and statement. And the determination of whether they're sweet or savory in this case has to do with our measurement of them. Right? It has to do with us and our representation. When we say that an electron is sweet or it's savory, and that 50 of them are sweet and 50 of them are savory, that's a limitation of we're projecting our own macroscopic bias onto the system. It gives you the wrong answer, or it's very confusing. So what we're going to treat electrons are as superpositions of these properties. So it's not that, let me write this on the board instead. Okay, so electrons are not 50% electrons that are sweet and 50% that are savory, okay? Like you have two different distributions. Like you think of it as two different molecules, right? You have some sweet ones and you have some savory ones, and there's 50-50 of them at all times, and they're randomly distributed. This gives you the wrong answer, right? This is what screws us. This is not what they're like. So electrons are not this, but rather an electron, not exactly, but I'm going to say approximately, is equal to sweet plus or minus savory. And the actual electron is a combination, or a superposition, as we call them, of the sweet state and the savory state. They're both at the same time, always. They have both properties. And what we're going to find out is that it's not, so here's the difference. When I write it like this, think about it chemically, right? You have a chemical distribution of sweet electrons and savory electrons. They have no energy difference, so you get 50-50 at all temperatures. That's the wrong way to think about this. Instead, every electron is both sweet and savory simultaneously. And when we measure the flavor of the electron, we write that very carefully, measurement leads to 50-50 probability of observing. Sorry, I ran out of space. Okay, so chemically, classically, the way that we got wrong, where we got all the wrong answers here, is that we have a thermodynamic mixture of sweet and savory, 50-50. That's not what it is. All electrons, before we measure them, are both sweet and savory simultaneously. They can be plus savory or minus savory. Don't worry about the plus or minus. You can just take positive and negative contributions. We'll talk about that. It's very important, but not important right now. You can either add them or subtract them, or however you want to do it. And when we measure the electron with our apparatus, the 50-50 doesn't tell us how many are sweet and how many are savory. It tells us what's the probability of observing an electron being sweet or savory. All right? So the property of an electron is that it's sweet and savory. It's just that when we measure it, there's a 50% chance of getting one or the other. We can't measure it being both. We can only measure one result. Right? There's no line that gives us sweet and savory together. We just get sweet or savory out of the box. So that measurement, the probability of measuring a sweet electron is 50%. The probability of measuring a savory electron is 50%. But the electron itself is both sweet and savory simultaneously. And when we do the measurement, you get one or the other. That's the key difference between quantum mechanics and thermodynamics. Thermodynamics says that there's 50-50 sweet and savory. Equal mixture. 1 mole of each. But quantum mechanics says it's both simultaneously. That an electron is a sum of a sweet state and a savory state. And our measurement leads to either one or the other at 50-50 ratio. That's the important distinction. And that distinction we're going to dig into deep this semester because it's critical. These are very, very different worlds. Very, very different worlds. And we have, and for instance, this doesn't tell us anything about, can I take a sweet and make it savory, for instance, right? From far as I can tell, I can't make a sweet and turn it into a savory this way classically. But it turns out if I treat my electron like this, where it's both sweet and savory, it turns out that I can actually take a sweet electron and turn it into a savory electron and vice versa. That's what this result leads to. These are ephemeral. They exist, I wouldn't say they're ephemeral, they're always sweet and savory, but the distribution we can actually manipulate it so that we can take a certain set of electrons, for instance, and prepare them in a system where if we measure them, we get 90% sweet and 10% savory. We can make them more sweet, and we can oscillate it in time. All right? Well, we're not going to do that with sweet and savory, obviously, but with spin we will. This idea that we can convert between one or the other in time. This is, and in fact, the interesting thing is that this concept, this idea that an electron can be two things at the same time and you can manipulate it, the distribution of sweet and savory in time, is the principle of nuclear magnetic resonance spectroscopy, NMR. That's what NMR does. It uses the sweet and savory characteristics of the nucleus of a hydrogen atom, which has a spin, and you can manipulate that spin to convert it between, in that case, spin up and spin down is what they say for spins, but between sweet and savory for that proton. And you can do that with light, right? And if I assumed that my distribution of sweet and savory electrons was like this, like a thermodynamic mixture, 50-50, couldn't do that because the sweets are separate from the savories. There might be a chemical reaction that converts between the two, maybe. But that doesn't, but the experiments show that that's wrong, right? I've just shown you that this is completely incorrect. Leads to the wrong result. But when you assume this, it's complicated. It doesn't make a lot of sense yet, but it gives you the right answer. It gives you the right answer every single time to insane precision. All right, we'll talk a little bit about the electron later. You can measure properties of the electron using this assumption to precisions you can't even imagine, right? So for instance, in thermodynamics, when we measure temperature, we go into the lab upstairs, measure temperature, the best you usually can do is about 1/10 of a Kelvin, right? About maybe 3 significant digits or something like that. You can measure things about the electron, making this assumption and doing a little bit of theory, a little bit of physics, just very basic physics of electrons. You can calculate properties of the electrons to 12, 13, 14, 15 significant digits without even breaking a sweat. That's how precise this is. It's one of the most precise theories ever invented. And the important distinction here is that we're going to start treating objects that have different properties, not as distributions of those objects with those properties, but rather that the objects are all the properties at once. And the thing that determines whether an electron is one property or the other is our eyes. Our measurement device picks it. Right? When we measure it, we get one or the other. But in fact, the particles themselves are all of their properties simultaneous. That should blow your mind a little bit. It should be really confusing. And there's no reason for it not to be, because this confused people for a very, very long time. It's a miracle that here in 2023, I can teach this to undergrads. Because 100 years ago, the only people who understood this were people like Einstein and Niels Bohr and Linus Pauling. You know, it was in 1920 that the first quantum mechanics textbook for chemists was written by Linus Pauling and Ernest Bright Wilson, who's a professor at Harvard. And it was the only book in the world built for chemists in quantum mechanics. And now we have more. That book you can buy for $5, but and it's not very good anymore. But in 100 years, we've gone from a technique or a theory that only 50 to 100 people understand to being able to teach to you guys pedagogically at this level. You can't say that about any other theory, right? Think about calculus, for instance. Calculus didn't become important at the college, at the undergraduate level, probably until the early 1900s, maybe the late 1800s. But of course, calculus has been around at that point for almost 400 years, 300 years, right? Leibniz came out with calculus in the 1600s, early 1700s. Right? So calculus had been around for 200 and 250 years before it became common. Quantum mechanics, we were learning it 10 years at the undergraduate level. We were learning it 10 to 20 years after it was first invented, right? And the reason why that is not because our standards have increased, though they have. It's because it's actually not that complicated. It's actually really, really simple. The problem is training your brain to understand it. Right? The math itself, the physics, is very simple, very elegant, very beautiful. But getting yourself away from this idea of things having defined properties, and electron can only be one property always, right? Just like, right? That things aren't fluxional. That's the wrong way to look at things. You have to pull yourself out of that and to start thinking about objects being fluxional as existing on a continuum. Right? Electrons were doing third wave feminism and gender studies way before we ever were, right? Things are on a continuum for electrons. There's no defined gender for electron. They can be either one whenever they want, and you can change it as you will. Right? It's very, very powerful, but just like with gender, it requires a different way of thinking. A different way of thinking, and we're going to find out that theory is the way to do it. Okay, I'm out of time. So what we're going to start with next class is we're going to continue on this trajectory. We're not going to start with theory yet. Again, I want to talk about history. All right, we're going to talk about why quantum mechanics is necessary. You've seen one example of it here, and this introduces this concept of superposition. There are a couple of other new concepts in quantum mechanics that we have to think about. And so I'm going to teach you guys about some other experiments over the last 100 years or so that illustrate these other concepts that are essential for QM. And then I'll let you guys play with them on the problem set. Okay, have a lovely weekend, everybody. Thank you for coming. I'll make sure to have everything from today on Canvas in the next couple hours. Thank you.